Testing 1, 2, testing 1, 2. We're on. Thank you so much. Oh, goodness gracious. But now it's preserved for all of eternity or whatever YouTube goes out of business, which might as well be eternity. All right. How are we doing now? Good. The second time's a charm. All right. So Nick, our dear TA, is posting a quiz. That'll be a little review of neural networks, just to make sure you do a little extra review there. Due Friday. Multiple choice, friends. It's okay. It's okay. Open book, just not open neighbor. Okay, you know the rules. Okay, all right. Another way, just make sure you get topped off quiz score. Good to have. Easy points. Easy points. So last time in lecture we were covering reinforcement learning, right? Anyone want in their own words tell me what reinforcement learning is all about? Anybody? Yes. You fidgeted too much. All right. Yes. You. Yes. Maximize a reward function. Exactly. That's a key part. All right. That's a key part of reinforcement learning, that you have a reward function that you want to maximize, that you have a policy that maximizes that reward function, right? Okay. But critical to it is the fact that you have an agent, a thing that's using a policy interacting from the environment, and the environment is the thing that gives back that reward function. Okay? Now, I want to go into more mathematical details for the implementation of value iteration, policy iteration, because I want to code that up on Thursday, okay, actually in Python, so you can actually see it from scratch. We covered sort of generally, but we had shockingly few equations, okay? And in addition, this is a fascinating course. I say that as the guy who made it, so I'm completely unbiased, right? But machine learning, this thing that we're doing, okay? We have been doing machine learning as predicting data, as in supervised learning, clustering, a little bit of clustering, reinforcement learning. But we didn't even talk about some of the math that underpins all of it. We talked almost nothing about statistics and probability, okay? And that in part was intentional, because not everyone here has had a course in statistics and probability at this point in mechanical engineering. You didn't take their statistics. Isn't that your 5th math requirement or something like that? You could do something else for it, right? But I am determined to show the world that you can do machine learning without knowing what the statistics and probability are, okay? And we've done that for approximately 2/3 of the class, okay? But I'd be remiss if we didn't spend at least some time going to just some of the basics, just a little bit of the basics. If you're a grad student, this is probably going to be very boring for the first, 5 minutes or so. But just because these equations we're going to be using for reinforcement learning are going to necessarily require things like expected value, okay? It's not that much, and probability distributions, and that's all I want to talk about. And then also really bringing up the fact that if you look through the deep learning textbook by Goodfellow, okay, there are the actual theory underlying why machine learning works is all about probabilities, okay? If you think about it from a high level standpoint, that actually makes sense, because you're creating a model. What are the 4 things you need to set up, your machine learning algorithm? Your model. I'll shake my hands a lot. Data. Optimization algorithm. Cost function, right? Okay, right. So you have this model that's job is to somehow predict data or something having to do with learning from data, right? But whether or not it's actually predicting data, it's a bit of a guess. Or to say it more mathematically, it's probabilistic. It's a probability. I mean, so all of the math that says, hey, this should work, fitting this algorithm to this, fitting this model to this data has this probability of predicting the new data set. That's all based upon probability theory. And also information theory, okay? We have not explicitly gone into information theory, but it is its own can of worms. And if you're looking at any papers that really theoretically dive into the underpinnings of machine learning, you'll come across information theory, okay? And you know what? I'm going to tell this story. Has anyone ever heard of Maxwell's demon? You have. Do you know anything about this Maxwell's demon, or you just heard of Maxwell's demon? You know enough. You're going to spoil the story if you go any further, okay? And you all are mechanical engineers. You're the perfect audience for Maxwell's demon, because you're talking about cold and hot, is what you said in the audience right there. It's about separating cold and hot. We have all taken thermodynamics, my friends, right? So you have encountered the phrase enthalpy, entropy, okay? Yes, I'm seeing smiles and some frowns. I think it's appropriate for thermodynamics, okay? All right, this is going to be story time as we build into some of the math, okay? Because we won't talk too much about information theory, but this is how cool it is, all right? So, my friends, as mechanical engineers, okay, let's say you have a box of air, okay? And in that box of air, on one half of the box is hot air. The other half of the box is cold air, okay? And then you let it go. What does it do? It all mixes together and becomes warm air. Exactly, right? That's just thermodynamics, okay? And if you look at this from an entropy standpoint, okay, you go from this very sort of ordered thing where you have hot on one side, cold on one side, and then they mix together, okay, and the entropy raises, I believe, okay? Like basically, there's a reason, will on its own accord, all that warm air that's now mixed suddenly separate the cold and hot air. No, that's fundamentally thermodynamics. We learned that in mechanical engineering, that would actually be a reduction of entropy in the universe. Is that possible, friends? No, it is not, right? And you're like, where's this going with machine learning? Just you wait. Just you wait, okay? So yeah, just like your fridge won't spontaneously become colder once you shut it off. It requires external work in order to pump hot air out of the fridge and then refrigerate it, right? Or I forget how a refrigerator works. I just drink things out of it, okay? But it's been a while since I took thermo. But there's this fundamental conservation law of thermodynamics. Number one, thermodynamics is the study of energy, and energy can neither be created nor destroyed, right? That's number one. Energy is conserved fundamentally, right? Yeah, good. Two, entropy. The whole total entry of the universe is always non-decreasing. It's always, at the bare minimum, either staying the same or going up with every process involved. Like, fundamental. It is so important that, like, if you have a physical concept, like in astronomy, if you discover some new, like, black hole thing, and people are doing the math and says, this violates, the second law of thermodynamics, you got a problem, right? Then Stephen Hawking has to write a thesis, like literally write a thesis to say why this doesn't violate the second law of thermodynamics, okay? And I'll get around to that as well. Oh my gosh, this is going to be a very ambitious part of the lecture about machine reinforcement learning. Okay, so back to this idea of the box full of air. Cold on one side, hot on the other side, okay? Now, put a barrier down the middle, perfectly insulating, which is assume it's perfect insulation on all the walls, okay? Now, this should theoretically stay cold air, hot air, right? Following along. Now, in the middle of that center, we're going to do this okay, here. We're going to start drawing. Drawing is an important part of the process. Okay. All right, this is for fun. It's for fun. Okay. So you got cold air, brrr, hot air, hot. You got wall down the middle, perfectly insulating, right? Okay. Now, I am going to put a little door in the middle. Okay, let me just put a little door, okay? Little door, happy little door, okay? It can open and close. Let's just assume it's just infinitely, it's infinitely, light, theoretical insulator, infinitely light, infinitely insulating. You can open the door for almost no energy at all. Beep, 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 beep. Just say open up, open, close, right? Okay. Now, hot air, as we all know, that's faster moving particles, right? That's what temperature is. It's the average kinetic energy of particles in a space. That's what temperature is, okay? And cold air is slower moving. These are little arrows. These are little vectors indicating how fast it's going, right? Okay, look, they're so slow. They're so fast, okay? Now, I'm going to create a demon. Name's Maxwell's demon. I don't know why he's subservient to Maxwell. We'll leave that for another time, okay? But this demon, it operates the door. Okay? Operates the door. Okay? And when it sees coming on this side, you know, there's a distribution of these particles, right? Some are a little faster than others, right? Faster. If it sees one of the faster cold particles come by, and it's going to go through the door, opens the door, lets it through, shuts the door. Now, it also looks at the other side. What's coming my way? Oh, here's a one of the slower of the fast particles. Oh, okay. I'm going to open the door, shut it, let it go through. I'm going to let the slower things go to the cold side, and the hotter things go to the hot side. So this demon, it's going to keep heating up this side, right? Faster and faster particles are going there. Slower and slower particles are going there. It's going to get hotter, that's going to get colder. The thermodynamics like that? No, thermodynamics is not like that. How is that possible? This is a thought experiment. But nothing I said so far breaks the laws of thermodynamics. Yeah, you could have a really, really, really tiny small door. And people will say, well, no door is infinitely light, and no thing is perfectly insulating. Those are all cop-outs. Cop-out answers to the paradox of Maxwell's demon. If you this demon is smart and can let fast particles go to one side, cold particles go to the other side, guess what? Free energy. So we just got to mine the demon for free energy? Or is there another reason that this does not violate the laws of thermodynamics? Okay? Enter a scientist named Claude Shannon who worked at Bell Labs, who were studying these kinds of systems. No, not demons. Information theory. And he was talking about this problem. And he came up with a solution. He said, actually, the demon is using information to make the decision as to whether or not the door opens and closes. Okay? And he went and did the math for like the amount of like of how the demon would make a decision. Not a demon. I stopped talking about the demon. But like the fundamental units of information it would need to know to open and close a door. And he found in the math that he was finding the equation for information that it would use to make yes-no decisions is exactly the same form of the entropy equations. Okay? That yes, you are lowering the entropy of this whole system by separating more cold into hot. But how is the balance of entropy rectified? The fact that information is actually a physical quantity that counts for the information of the universe. Okay? That sounds wild. And you have every right to call BS on me. Okay? But this information theory, this actually means that there's such a thing as conservation of information. Okay? That doesn't mean that if you take your homework and you light it on fire, that information is no longer conserved, you know, like that information is in the flame. But like it means information, a very specific quantity, okay? And it's called Shannon information, after Claude Shannon, or entropy-based information, okay? So so there are conservation laws and real mathematics as they pertain to information that are just as fundamental as thermodynamics. All right? Is that wild? Okay, that has nothing to do with dynamic programming today. But the point is that information theory is a real mathematical discipline with real conservation laws, such as information can neither be created nor destroyed. Okay? And this has real implications for astronomy. Okay? A black hole. Send something into a black hole. It's never coming out. That should destroy the information. Well, that violates this conservation law of information. I'm being a little loosey-goosey with some of the details, as you're imagining, because it's not an information theory course. But that was a real problem. Like, wait, information theory is so fundamental, there must be something we don't understand about black holes. Something must be coming out of the black hole. That information cannot be destroyed. Turns out, black holes gently radiate. I don't know exactly what. I didn't study for this part of the lecture. They have gentle radiation that comes off of them. that actually encodes this information in this weird encrypted way. Not a real encryption, but like in a way that's just hard to recover, right? It's called Hawking radiation. Stephen Hawking proposed this solution, okay? So that's how deep and weird and wild information theory goes. And there's all kinds of cool things like, how you define information. And there are many metrics. What the classic conundrum is, classic conundrum is which has more information? The letter, which has more information? The first 100 letter A's all in a row. 100 random letters from A to Z. They're random. Or the first 100 letters of Shakespeare. Okay? Shakespeare. Is that how Shakespeare writes? He just writes his name over and over again. Shakespeare, right? Which contains the most information. And by some metrics of information is quantified by how well they can be losslessly compressed. Okay? So this doesn't contain much information at all, because you could just say A 100 times. Shakespeare seems like it's a lot of information, but you can still compress the words down to maybe other ideas, that are slightly compressible. But completely random 100 letters, you can't compress that at all. There's no pattern to compress. All completely random. Okay? So again, that's all to entice you to look more into information theory at some point in your lives. There's actually a pretty cool book. It's called it's called Fortune's Formula. It's not a textbook. By William Poundstone. And it covers, and William Poundstone does a lot of these books that are about math, but not about math. Okay? And what he wrote about was this is all about scientists trying to get rich off of gambling. Okay? So, and Claude Shannon was one of the people. He went into a casino with a computer in his shoe that was going to read when the roulette wheel would stop and place bets on it before it stopped. It's pretty cool. But one of the key elements they talk about is information theory, and also forms of blackjack betting. Anyway, this has gone off the rails, but it's really cool. Really cool. So this hopefully will entice you to read the information theory section of Chapter 3 of the textbook on deep learning. Okay. Also Chapter 3, Goodfellow. Chapter 3. Okay. Just a little background. In probability, which is the first part of that chapter. Okay. Did everyone already know that story about Maxwell's demon? Do they teach that in 5th grade now? I don't know. These are very competitive schools they have now, I understand. So, all right. So, a little background in probability. Things we got to know. Okay. So the idea of probabilities, that probabilities P of x is always less than or equal to 1 and greater than or equal to 0. Now that's certain. That's certainly not. Okay. Okay. And you can have a distribution of probabilities. This can be a distribution of probabilities. That you could have x, and you could have p of x, lowercase p of x. That's a classic one. That's your normal distribution, normal / Gaussian distribution. Gaussian distribution. Okay. But it can be any kind of shape that you want. The only thing that you have to be able to do is say that the integral of p of x dx from minus infinity, that's an 8. That's an 8. Minus infinity to infinity has to equal 1. That's just saying something's got to happen. Okay? Like I said, this is the mathy lecture. We use those kinds of precise phrases. Okay? We also have to talk about expected values. Okay? If you play blackjack, as I do from time to time, and I don't count cards. Yep. You are often gambling on the expected value of what happens if you hit at the blackjack table, for what happens if you stay at the blackjack table or double down at the blackjack table. Okay? And so the way you would compute as to which one's better, you're looking at what the blackjack is not part of the required reading here, to be clear. But you look at the options that the dealer has, what kind of hidden card they might have. You say, okay, here are all the probabilities. Here's the probability of everything that they've got. Okay? And here's the probability of everything I could get when I hit versus when I stay. And you say, okay, here's the probability of all these things happen. Multiply it by how much I would win. Okay, and compare that to what are all the what's the probability of all these things happening if I stay as opposed to hitting. Okay, what's the probability I'm going to win there, and how much money, right? And you compare that. That's your expected, and so each of those things are your expected value. How much are you going to return? What's your expected return? Okay, so expected values is just taking all the probabilities of probability of this thing happening times the outcome plus this thing happening times the outcome across all of these different across all these different outcomes. Okay, so the expected value, little fancy e, the expected value of x across some probability distribution p f of x across f of x, which is your return, thing that you hope to happen, things you think will happen, is equal to the sum across all the possibilities, x, the probability of each of those possibilities, times the value f of those possibilities, right? And because all these probabilities should sum to 1, it's going to be some kind of weighted average across f of x. Okay? That's for a discrete, because it's a sum, it's discrete. Okay? If you want it across a continuous it's going to be an integral. Capital P of x, sorry, lowercase p of x, f of x, dx. So that's a discrete, and the capital P is a discrete probability. Lowercase p, whoop, lowercase p, that's a continuous probability. Yeah, there you go, expected values. Those are really important for reinforcement learning because you want to know, if you take an action, what's the expected reward that you're going to get from that action? Okay? So that's the world's silliest probability lecture. I'll just give you a couple other nuggets, right? Does anyone know the definition of variance? Where it comes from? People know standard deviation, right? People have heard this, heard of Spanish. I've seen blank stare. Yes, okay, thank you for nodding. Okay, make sure this mic wasn't disconnected, you know. So, right, we all know standard deviation, but where does it come from? And where does variance come from? Well, variance of some function of x, it's the expected value of the expected value's difference from what you found. Okay, it's like the expected value of the expected value, in a sense. It's the expected value of f of x minus the expected value of f of x. Okay? And you square it. That way, if it's perfectly balanced, your variance isn't 0. Okay? If it's super spread out, that's a high variance, right? Even if it's symmetric, right? So you square it so everything is positive. All right? And the standard deviation is equal to the square root of the variance of f of x. Okay? So now if you have multiple variables that you're looking at, your question. It's the entire expression. So you can't, so Angela, you're sort of saying, hey, can I square root and get this rid of that? Is that what you're saying?
No, I think you should have like an extra.
Oh, did I screw up a parenthesis? Okay. Yes. Oh, thank you. There's got to be an extra one there. Thank you. That's why Python's normally there to yell at you about that sort of thing. Thank you very much, Angela. Claw clap for Angela. Claw clap, claw clap, claw clap, clap. Claw clap. All right. So, all right, thank you. Sorry, I missed an extra parenthesis. Sorry, I thought you were saying something else. All right. So, if you have multiple distributions, you have multiple variables, multiple things that you're measuring, you have f of x and g of y, you could say how much they covary, or their covariance. That's variance. This is covariance. COV of f of x and g of y is the expected value. That is a silly expected value. All right, of f of x open parenthesis f of x. I don't want to, as much as I love being corrected by Angela. I'm going to move this down to the next line here so I'm not going to squish. Okay. Minus the expected value of f of x times, parenthesis, g of y, the expected value of, minus the expected value of g of y. I think that I need a close bracket. Does that pass the Nanaj test? Good, thank you. Good, all right. So you can multiply these vectors together. What actually ends up happening is it creates a matrix, covariance matrix. That gives you an outer product. And so you can see how it creates a matrix that looks like this, and how much one varies with the other, So it's a matrix. It's a matrix. Okay? Let's look at the dime store, just probability, just as a reminder. So I'm throwing out expected values, and it's been a little bit since you've seen them. Okay? Any questions so far while I grab this conspicuously placed swig of water? Thank you. Question? Yep. Stop me. What are you looking for? This thing? Or this thing? Okay. Yeah. So for a given x, there's a probability that something will happen. Okay, and a capital P is a discrete probability. So here we'll do an example in red. So let's just say your probability distribution, okay, looks like this. So this is P of x. And this is 1, this is 2, it's 3. And it's like, right? Looks like that. So if you put in x equals 1, it'll give you this probability. X equals 2, this probability. X equals 3, this probability. Okay? Take all three of, if you take all three of these values, they should all sum to what? 1. in all of my classes, about 80% of the time when I ask you what the answer is to a math question, it's either 0, and then the other remaining 15% is like 1, and the remaining like 5% I'm tricking you. Okay? Yeah. So here, so for this particular event, event 1, there will also be, I'm running out of room, some f of x, where on this axis it's x, to be clear, x, 1, 2, 3. And these could be any set of numbers, right? They don't have to sum to 1. These are some value, like that's 10, that's 5, that's 15, clearly not the scale. Okay. So if this was a probability of 0.5, if this is a probability of 0.75, this is a probability of, wait, whoa, I'm screwing up already. Oh, math ain't mathin'. Let's just make this 0.2, 0.5, 0.3, not the scale, right? It would be 10 times 0.2 plus 5 times 0.5 plus 15 times 0.3. Okay? Right. Now, if you had, to our linear algebra friends, and I'm writing this, for expected value, or for expected value of some expected value of some f of x, if it's discrete, meaning like I'm drawing it as bar graphs and not a curve, right? If we're a curve, woo, that's continuous. Okay? You could do this as you're having one element times another element, plus another element times another element, plus another element times another element. Is there a fancy way to write that in linear algebra to make that like super compact? What? Inner product, did I hear? Dot product? So you can compute as an inner product. As inner product for discrete. So if you had f of x, what were my numbers up above? Anyone remember for f of x? 10, 5, and 15. And what were my numbers for p, capital P of x up there? 0.2, 0.5, 0.3, right? Okay. So you could say, hey, my expected value is the inner product. I want it to be, it's going to be a scalar number, so I want it to be a 1 by 1. So I'm going to multiply it. This is a 1 by 3. This is a 3 by 1. This is a 3 by 1. If I turn this to a 1 by 3, multiply it by 3 by 1, I can multiply them. Those dimensions degree. It results in a 1 by 1. Therefore, I could say, hey, f of x transpose times p of x. Well, look how nice that is, right? This is a math trick. Might have to use that on Thursday. Might not. We'll see. It's exciting. Who knows? Maybe we'll get another lecture on Maxwell's demon. You never know. Okay? Okay. All right. That's your probability lecture. That's the probability we need. Okay? There's conditionals probabilities. There's Bayesian probabilities. We will cover that when we need to. Okay? But, well, actually, I'd be mad if I didn't talk about Bayes' rule. Sorry. All right. Conditional probabilities. Okay? The idea is that probability of x happening, given that y happens, is equal to the probability of x happening of the times the probability of y happening given x all over y. Okay? That's Bayes' rule. The idea is that you can multiply this on the other side, and it looks like this. The probability of x happening given y times the probability of y is equal to the probability of x happening times the probability of y given x. Okay? But this here is Bayes' rule. Okay. So if you are talking about machine learning in a broad sense, okay, that the probability that maybe your model captures this data is conditional on the fact that you have data in a certain distribution, okay? As people talk about these distributions, so probability distributions, okay? Most common, the normal distribution, that x, probability x, given that you have some mu, which is a mean, and some variance, which is sigma squared, okay, equal to 1 over 2 pi sigma squared times e to the power of minus 1 over 2 sigma squared, quantity x minus mu squared. And that gives you your bell curve, right? Okay, that is your mean. This is your probability, p of x, under lowercase x. That's your variance. The variance, because sigma is the standard deviation, therefore the variance is sigma squared. Okay? There will be all kinds of proofs that say, assuming a normal distribution. They mean that. Okay? If you talk about machine learning more generally, okay, let's say that here's x, here's some probability of x, and here is the probability distribution of your training data. Okay? Now, when we do our testing and our validation of a model, the assumption is to know that we have trained this properly, that our, I'm just drawing a little temporary marker here, that our validation data and our test data is the same distribution, right? Okay. Now, that's not often the case. Sometimes you can get a different distribution. What if you had a different distribution over there, right? You are trying to test your model out of distribution. Okay, so there is this buzzword. It's more important than buzzword. It's a fundamental concept. Is that if you are trying to implement your model, deploy your model in an out of distribution setting, out of distribution environment, bad things can happen. How bad can they get? They could get really bad, but there's a whole theory. People like, oh, if you have this kind of distribution, you know, in this kind of distribution, this is how certain you can be. It's all very theoretical. There's a lot of people working in this field. The idea is you can have out of distribution concerns. Let's say you had, like, this is your test data. Your test data. So there's a reason that when we are setting up our test data and our training data, or when you did your homework, you grabbed a certain number of values that are training and test, right? You try to grab them randomly from the whole data set in hopes that it preserves the distribution. Okay? All right. So probability theory is extremely fundamental to machine learning. But we've been getting away without using it because we've been very much applying it. It's like, here's the algorithm, here's the application, code it up, show me you can do it. But this is what makes it work at its core. Okay. Now back, my friends. Let's return to reinforcement learning. For RL. Okay. So, recall we have something called an agent that has to interact with an environment. Okay. And that agent performs an action. Okay. let's call it A sub t for at the current time t time. All right? It performs an action on that environment, okay? And that action might change the state we have in that environment. So we'll call that S t plus 1. So like something happens, we are in a state t, we're now move on to the next time, t plus 1. And also, we can measure our reward. We'll call it R t plus 1. That's our reward. That is our state. Okay. Then we take those rewards and we send them off to our agent, and we send them off to and we send the states off to our agent as well. So we'll just call this ST now. Now it's the current time. We've moved forward in time. We move on with our lives. Okay. Cool. Awesome. So now we talked about this idea, so these core concepts. You have reward, R, you have state, S, and action, A. And remember, we were doing this in grid world. We were having so much fun walking around in these squares. Well, I did all the walking because I need to get my steps in. Okay? For each of these squares were our states. And the action we would take would move us from one square to the next. We even drew some alligators for fun, just to taunt our rivals. Okay. UF joke. Yeah. All right. So now, the idea was that when we have a reward, okay, that reward is going to be dependent upon the state that we're in, the action that we take, and the state we end up in, or more importantly, the state we end up in, okay? So, and the fact is, an action that we may take may not deterministically, meaning for sure, take us to another certain state. There might be a probability of them, right? We talked about this as a Markov decision process at the end of last lecture, okay? So, now, let's write out. So the probability, we'll say that state S, and we'll say S prime up here, S prime, that's the next state. Okay? The probability of S prime of a certain reward given, well, given you're in a certain state and action, is equal to the probability that the current state ST plus 1, the next state, I'm sorry, equal to S prime, R plus 1 equals R, given that ST equals A, and AT equals A. This is all in the same line. Don't let your eyes deceive you. Okay? And this is just setting up, this is the notation. Okay? That's the probability of S, of a reward given a state, and an action that you've taken. Okay? This is just saying that, hey, the next state is equal to S prime, the reward is equal to R. Did I say ST is equal to S, not A? I apologize. That's a typo. All right? I'm sure you all caught that. Okay? Right. Okay. These quantities completely specify the dynamics of a finite Markov decision process. Again, that's the idea that you has all the information that you need is encoded in the state and the actions you can take. All right? Now let's talk about rewards. Okay? If you are in a given state, again, back to my grid example, okay? If I'm in this state and I take a certain action, I should know what the reward's going to be or have some probabilistic estimate of what the reward's going to be. Even though that action might not take me there, it's possible I set up my game such that maybe I could be tackled by an errant football player. I could end up over here instead, or more likely, the hospital. Okay. All right? But it might not end up in the same place every time. So we need to talk about reward in terms of expected values. What do we expect to get from that action? So our reward, we define reward is dependent upon your current state and the action that you take in that state equal to the expected value of R plus of your, so that's your that's the reward that you will get given that you're in ST is equal to S and your action, your current action, and that's equal to the sum of the reward across all rewards, capital R. We'll do it's a fancy script R. Excuse me. Give me a second here. Whoa. There we go. Fancy script R. Okay. Fancy script R. Basically, across all rewards, R multiplied by summing across all of S prime. That's the next state. That's where you end up with. Across fancy S, that's not a delta, that's a fancy S, right? For fancy S, whoa, there we go, fancy S. Okay? The probability of S prime of R given S and A. So here are the probabilities that you'll end up in some next state. And you sum it across all your next state and we multiply it by the reward of ending up in that state. Okay? Again, go back to my example here. I am here at this state. Let's just say I want to take the action to move forward. 50% chance I hit where I want to go. 25% chance I end up there by an errant football player. 25% there by errant cheerleader. Okay? Reward here, 10. The reward here, 4 and 4. So 50% times 10. Plus 25% times 4, plus 25% times 4. My mental math says 7. My expected reward is 7. Yes. Right. So that's all that's saying. But it's saying it in math, right? And if we say it in math, it means we can rewrite it in things like nice vector calculations, the outer products or inner products, inner products, whichever applies. Okay. All right. So we also have our state transition probabilities. That was the gator from last time. Okay? The gator with the frog that was going to jump in its belly. The state transition probabilities. Okay? You got P S prime given S. Basically, it's a probability that if you're in S, that you end up in S prime, given you take an action. Okay? That was literally my example with the stepping forward, tackle example. Okay? Equal to the probability, so is equal to the sum of R is in the fancy R. That's a fancy, I'm going to do it nicer, fancy R. Okay. All right. Across all your rewards, probability S prime of R given S and A. Okay. That's straight transition probability. I need a sorry, Angela, I heard you in my brain. Heard it. We're psychically linked. Okay. All right. Okay. And so then we have the expected rewards. Okay. Across. So here, this was the expected reward for a given state and action. Okay. But the expected rewards, this means that it says, hey, R, S, A, and you take into account where you're going to end up next, S prime. It's going to be equal to the sum of R is all in fancy R, all the possible rewards, of reward times probability that you end up in S prime of reward given S of A, all over the probability that you end up in the next state given the current state and action. Okay? All right. Okay. So we also talked about this idea of value and value functions. Because while we might have a maze problem where I might say I start here, I want to end up over there, the reward is there, there's no reward over here, what do? I'm lost, oh my goodness, I have no idea. The idea is you set value to different states. Okay? And what's the math for that look like? Okay? So, call the value function V sub pi, meaning for a given policy, pi, okay, of S. So every state has some kind of value. Okay, is the expected value for that particular policy of the sum from k equals 0 to infinity. Infinite sum, that sounds scary, right? You're not. Of gamma to the k, r t plus k plus 1, given your current state is S. You're in your current state. Okay? What does that mean? This is a fancy way of saying that gamma, that's the discount factor. Talked about that last time. We said it was 0.9 in our example. So the idea is that, in principle, you say, hey, I start in this current state, S. My value is me taking my policy pi and trying it out for infinite steps into the future and adding up all the rewards from them, but I discount them by 0.9 each time, right? So 2 steps in the future, it's 0.9 squared. 3 steps in the future, it's 0.9 cubed. And it's going to decay, 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 decay. All right? Okay. We call that the state value function. State value function. That's what V of pi is. Okay? But you can also have a value, what we call the state action pairs. Okay. We could also, so that's called Q sub pi. SA, Gesundheit, expected value of pi, and it's again the sum from your current step k up through infinity. Now you can't do infinity, of course, but that's okay. That's where we approximate it. Of gamma to the k, of r of t plus k plus 1, given that you are in S of t is equal to S, and you've taken a current action A. So it takes into account that you've taken an action. This is called an, so Q of pi is the action value function for policy pi. Okay? Recall that pi is the mapping from state to action. Okay? Put it in a state, put it in pi, you get an action. So your value will change if it can change if your policy changes, right? So machine learning methods that require the reinforcement learning methods that particularly iterate on Q, called Q learning, conveniently enough. It was the weirdest thing in the world. Back in like the 2023, 2024, there was so much hype over like ChatGPT. And it's still there, to be clear. It's also like propping up the economy right now with all the speculative investments, but that's for another time. I remember I was like on a social media platform, and like #1 trending topic for whatever my feed was like Q learning. I'm like, what? Was I felt transported back to like my master's degree when I was reading this textbook like in the corner office of like a basement. You know, I was like, what? And there was so much like there was all these rumors that like some massively intelligent machine learning model was going to come out, and it was using Q learning. Oh my gosh! And it was like, I never thought like, and like finance bros were like, oh man, dude, gotta get in on Q learning. Like, okay, sure, Q learning is great, but it's not that great. Anyway, that's cool. Anyway, all right. Such is life. Everything that used to be uncool, that I felt cool for knowing, is now cool. And I feel uncool for it. So, all right. Okay. So, all right. All right. So you can see the sort of the logic that's going on here, right? You have this idea of a value function that's taking out, like, that's basically assessing where we're going to end up. Like, and where we're going to end up, and saying what's the reward of ending up there, then multiplying it by some discount factor that discounts it down. It makes it less and less and less. You know. All right. So that leads us to a very important equation. It's super fundamental. It's called the Bellman equation. For V pi, for value. Okay? All right? So the value, that's a V, of pi of S is equal to, again, the expected value of the sum across all your time steps of gamma to the k, r plus t plus k plus 1, s d is equal to s. Okay? All right. Sorry, to get rid of that. Jump the line there. Okay? Now, naturally, you can't really sum across an infinite number of time periods. You can't really do that. Okay? That's not cool. Okay? So what you do instead, okay, is you say that, hey, this reward here, okay, that in and of itself, okay, so we could break this down where we could say that this reward is also, like, that's the expected reward for the next step. And that's going to be some other kind of sum within a sum. All right? So we're going to write this out here, the expected value. My E's are all over the place today. E, expected value, RT plus 1 for the next step, plus gamma, keeping in mind, you can pull out, so it's going to be gamma times the sum, k from 0 to infinity, we still got some infinities involved, that's okay, of gamma to the k, rt plus k plus 2 of s of t equal to s. We kind of looked at like, hey, a time step ahead, what's the reward going to look like? It's going to be the same sort of sum, but one step into the future, okay? K should be, well, given that it ends at infinity. I see the logic of that. The Bellman text, the text has it as 0. Good question, though. I don't have a full answer as to why it's not 1. That's a good answer. A good question. So in the audience, they're asking, why is that not 1? Because we pulled out a step, right? I'm not sure. Not sure. Okay. All right. So we can then take a lot. Oh boy, got a couple steps here. How much time we got? Not a ton of time. So through the Bellman equation, we find that if we sum across all of our actions using our policy, which is the action that you take given its current state, is equal to the sum across all of our next states in R of P S prime of R given S A. I'm going to give myself more space. I apologize if I'm bad at that. Sorry for your notes. Okay. Times R plus gamma times the policy, the value action of the policy at S prime. Okay. What did we just do? Okay. We are saying that our value here, and again, it's saying what's the value I have at being in this square when I get over there. Okay. Instead of having to infinitely sum across all the time steps in the future to see what will happen, I call that bad, right? We instead replace this infinite sum by saying, hey, no. Let's use as an approximation for the value across all infinitely many times in the future. This is the value function as we currently understand it at the next step, where we end up at the next state. This creates an iterative value approximation. Okay? That's the key. That V I of S. We update this based upon our policy, our value function based upon where we expect we will end up. Okay? This is called, it's the Bellman equation. Oh, you can't see that very well. I'll jump out. I apologize. Bellman equation. Or V pi, right? Okay? So if we want to update our value, this is the equation that we do. And these are finite sums. We say, hey, what actions can we take? We have some finite set of actions. In my example of looking at the board, like the grid world, up, down, left, right. 4. That's 4. Not so bad. Okay? Now for each of those actions that we take, all the states that we could end up in, we get the reward for each of those states we end up in. And what's the probability we end up in them? For that, we had that state transition matrix. That was the gator with the frog. Okay? That will help us there get the probabilities. We multiply it by the reward plus some discount factor times the value function we already have. What this will do is it'll update the value function. So we'll have a guess. Maybe it's all zeros. And then we just iterate over and over and over again, and it builds that value. Okay? That's the math behind that. And what else we covered today? We have 7 minutes, plenty of time. But the idea of this iterative value, right, is what's critical. Okay? Right? So how do we evaluate a policy? Okay. We use the Bellman equation. So given a policy, we use the Bellman equation to evaluate, hey, there's the word value, evaluate, get the value. And write this out. Evaluate a policy. Okay. All right. Okay. All right, and we can use it to iterate. So we successively update an approximation of the value function using v of k plus 1 is equal to the sum across all a's of policy s given a, some probability that you're going to end up in some next state s prime, r given a of a, so little space, okay, of a r plus vk s prime, extremely similar equation, the update. Okay, if you have something like a grid world problem, you can just look across all your states, a discrete problem, a finite problem. You can update it this way, okay? And that's what we'll code up. All right, we'll cover other elements of that when we go on to code it, okay? But this gives you at least a look at where all the expected values come into this, the actual math of it, right? But there are many problems where you can't just go through every combination like this, okay? So one thing that people have found is a good trick is that you will have something called actor-critic methods, okay? Where it's very hard to know what this value function is. You can use this method, but it only works for, like, I don't know, 4 states or so, roughly, in this sort of finite approximation. Like, it works really well for like up to 4 states, okay? But what you can do is you can use a neural network to represent a much larger space of options, right? So what people will do is not just use a neural network to represent a policy of in goes your state, out comes your action. They will also use a neural network to approximate the value function, okay? That every time let's say you have a policy, do this, then that, do this, then that, do this, then this, and that. You run it a bunch of times, right? You can see what the expected value is just from from trying all those things. Did it do well? What was the reward, right? But given that you ran it into the future a bunch of times, and you know what the reward was, and you have all these discount factors over time, you can say, hey, what was the value that we measured off of all those states, right? And then you use supervised learning to say, this neural network, that's the critic. That's the job of that neural network, is just to say, hey, that thing you did, that was valuable. That thing you did, not that valuable. It's not the reward. To be clear, the reward's much simpler. It's just grading you in the moment. It's did I end up in the result? Did I do the exact things that are good, that tell me that are good? But often to the hard into the future, that is hard to determine. But you can use a neural network, a deep neural network, to say, that's all right. You can build a neural network's only job is to assess the value of what you've done. Okay? Actor-critic methods don't require neural networks, but neural networks with actor-critic methods are one of the most powerful tools we have for reinforcement learning these days. Okay? Do you remember? People remember when we brought in the robot dog last time? Was that pseudo-memorable? Okay, good. I'm glad. I would go for it, right? Pseudo-memorable. Okay. When Jacob is training his method, he's using basically atom or stochastic gradient descent type methods, right? The loss function, the cost function, it's not just like maximizing reward. It's also all these parameters of a neural network that assess the value. It's trying to accurately approximate the value of this policy. So it's doing multiple things at the same time. Okay. And because it's updating the value and uses that value function to help guide the reward, it's actually a lot more effective. Okay? That takes us to the end of the class. We will be remote as usual on Thursday for a coding session. Hope to do some reinforcement learning. Thank you all very much.